3.1 Day 2 Exponential Growth. Write the exponential function with an initial value of 5, which decreases at a rate of 0.59% per week. So the amount is equal to the initial value 5 times e to the negative 0.0059 t. Suppose a culture of 100 bacteria is put in a petri dish and doubles every hour. Predict when the number of bacteria will be 350,000. So the number of bacteria equals 100 e to the kt. The number of bacteria will be 200 in every hour. So then when time is 1. Now if we divide by 100, we get 2 equals e to the k. And then we have to find out what k is. So on our calculator in y1, we can put in e to the k, or in this case, e to the x, and put 2 in y2. Now let's graph this with the standard window. So we'll go zoom 6. There's e to the k, or e to the x, and there's 2. And we want to find this intersection point. So we can go second, calculate. Number 5 is intersect. And we can hit enter, enter, and then we're close enough to that intersection point, it should find it. K is equal to 0.693147. The function is now n equals 100 e to the 0.693147 t. And now we're supposed to predict when the number of bacteria will be 350,000. Now we can plug 350,000 in for n, set that equal to 100 e to the 0.693147 t. And we can divide by 100. That knocks off 2 of these zeros. We have 3,500 equals e to the 0.693147 t. Now in y1, we can put this k in. So let's insert 0.693147. And in y2, we can put in 3,500. We'll have to change our window. One of our y's is 3,500, so let's do the y max up to 4,000. 4,000. And we'll go by maybe, I don't know, 200s. Let's graph that. There's the function e to the x, and it's going to go up this way, so we have to make our x values a little larger to the right. So we have window, how about, let's see if 30 is far enough to the right now. Graph. And there we see the two curves intersecting. So let's find that intersection point right there. Second, calculate an intersection point, number 5. And I can see the cursor is close enough right there. Enter twice. It says guess. I guess about right there. And so t is equal to 11.773 hours. Suppose the half-life of a certain radioactive substance is 20 days and there were 5 grams of the substance initially. When will there be 1 gram left? Now we have half-life of a certain radioactive substance is 20 days. So the number present equals the initial amount, 5, e to the k times t. It says the half-life, so we'll have half of what's present, in other words 5 halves, equals 5e to the k times 20. Now if we divide by 5, that'll be 1/2 equals e to the 20k. We're trying to find out what k is. In the calculator, we can put y1 equal to e to the 20x, and y2, we can put the half in here, and we'll see where these two intersect. Now this function hugs very closely to the y-axis because it's increasing very quickly. When x is 1, we'll have e to the 20, which is like 2.718 to the 20th power. It's a very large number. So even at 1, this is a very big value. So this is increasing very quickly. So in our window, we'll go from negative to 1 on the x values. That'll put us very close to the y-axis. And since in y2 we have a half, we'll make the y values -1 to 1 also. Let's graph this. There's the e to the x, hugging very closely to the y-axis, and there's the 1/2. And we will calculate their intersection, number 5. Let's get the cursor down a little bit. Press enter once for each function, and then the guess. K in this case is equal to -0.034657. The function is n equals 5e to the -0.034657t. When will there be 1 gram left? Now we can set this function equal to 1. So 5e to the -0.034657t. And we can divide by 5 to make it a little easier, I suppose. So we have e to the -0.03467t. And let's go to y equals. We can insert this k, -0.03467. And now I need to delete out the 20. And in y2, we can put 1/5. Let's graph this. Now we can see the function is up here and the 1/5 is down here. So our window is way too zoomed in. Let's go from -10 to, let's say, I don't know, how about 30? And we can go by 5s if you want. And then it looks like the y values might have been all right. Here comes the function. Let's see if it's down. It's still not below that 1/5. So we're going to have to go farther out on the x. Let's go from -10 to, let's say, 100. And maybe we go by 10s this time. Let's graph. Let's see if 100 is far enough out. Looks like that might do it. There's the 1/5. And so 1 to 100 was just fine. We'll calculate the intersection, number 5. Enter, enter. Here's the guess. Enter. And t is equal to 46.439, and this is days. The half-life of radium-222 is 38 seconds. You had a 12-gram sample. Write a modeling equation for the exponential decay. So the number present is equal to the initial value, e to the kt. And it says the half-life is 38 seconds. So this will be equal to 6 when t is 38. So we have 1/2 is equal to e to the 38k. Now e to the 38k is going to increase very quickly, so we'll have to go back very close to the y-axis. So in y1, we're going to put 38x. So let's delete all this out. We got 38x. And in y2, we can put 1/2 in. Now we need to get very close to the y-axis, so we'll go -1 to 1, and our y2 is at 1/2. So -1 to 1 should be just fine. Graph. Here comes the function, very tight to the y-axis. There's the 1/2, and now we can calculate their intersection. So enter, enter, enter again. The k in this case is equal to -0.018247. So n is equal to 12e to the -0.018247t. How many grams of radium-222 will remain after 76 seconds? Well, now this time they give us a t value. N equals 12e to the -0.018247 times 76. And of course, we're going to use our calculator to answer this. We can go just back to the home screen and type 12 times e to the -0.018247 and then times 76. Enter. And so we're looking at n equals 3 grams. Use your model to estimate when only 1 gram of the original 12 grams of radium-222 will remain. Now we'll set this equal to 1. And that's equal to 12e to the negative 0.0182407 T. So maybe you can divide by 12 and have this equal to 1/12. E to the negative 0.0182407 T. In Y1, we'll put this e to the negative kt in here. Negative 0.18247 x. And then in Y2, we can put 1/12. So we're probably going to have to go way out. Did I miss the point? I did miss the point. Let's go back up and insert that decimal. Enter. Window. Let's go from -1 to 100 maybe, and we'll go by tens. See if 100 is enough. And with 1/12, -1 to 1 should be just fine. So this really has to get low, down to 1/12. So it looks like 100 isn't far enough. So let's go to maybe 300. And maybe go by 20s. Graph. There, now we're leveling out almost to 0, so that 1/12 is right there. It looks great. We will calculate the intersection, number 5. Enter, enter, enter. And so T is equal to 136.229, and this is in seconds.